The definite integral. This is the lesson for today. Let's go through a review quickly, and then we're going to talk about notations and what that is. Now, you can pause the video and read what I have written right here as a review. But in the last lesson, I talked about the Riemann sum and the fact that there are infinitely many rectangles you can create under the curve of a function, and the area under the curve that is bounded by the x-axis, it can be approximated or it can be calculated accurately if there are infinitely many rectangles. Now let's go to Desmos, and I'm going to show you on Desmos a review. So remember that suppose we have this function. I chose this cubic function, and we have an interval from 0 to 2, and we want to find the area under the curve, approximate area under the curve using the Riemann sum. Now there are four subintervals, therefore there are four rectangles, right? But notice what happens. This is not very accurate. Obviously, we are missing this area for the calculation of the total area, and so is this area, and so is that. But if I move and increase the number of n, that means the number of subintervals that creates the number of rectangles, look what happens. The area under the curve is becoming more covered as we go, as n approaches a huge number. Now I maxed out here at 100, and you would see that this entire area is being blue now, it's colored blue, but that's still not accurate because there's still some areas. If I zoom in, you may see some areas, that area under the graph that is not covered. You see that? This is all these little steps right here, these small triangles right here. They're very small. It's still very accurate, but it's not as accurate if n approaches infinity. Okay, and this is what the Riemann sum is. And to make it very compact, we used this notation or this form. And this leads into what we call the Riemann integrals, and that is given by this notation. So the definite integral of f of x is defined to be the limit of the Riemann sum of f over AB. This is the interval AB, given that this limit exists. So if this limit exists, this is the notation. This is called the definite integral. And now we're going to talk about notation. What it is. We're going to look at the mechanics and take it apart and then explain each one. Okay, the first thing, this elongated S is actually the sum, all right? And then the A right here is the lower bound. Actually, let's call it lower limit. B is the upper limit. F of x, that's called the integrand. And the dx, that is the differential of x, and or is called the x itself is the variable of integration. Okay, so and that is the very basic notation of definite integrals. I need to make a note here so that you never forget. If f of x is continuous, so the function f of x right here, the integrand, then we say f of x is integrable. That means that you can take the integral of f of x. But the other way is not true. If the function is integrable, but the other way is not true. So if a function is integrable, right? But that doesn't mean necessarily the function is continuous. So you could have a discontinuous function, a function like a stepwise function or a rational function, but depending on which part of the interval you are actually doing the integration and using the value of the interval and subinterval to find the area under the curve, then you're going to be okay, but it's not guaranteed that it's going to be a continuous function. Let's look at one of the examples, and we're going to use the limit definition, and I'm going to show you how tedious this is, and that is important to go through at least one exercise using this long-handed form of calculating the area under the curve using the Riemann sum and this definition. Okay, let's go ahead. And here is the question right here. We have x dx. We're going to take the integral of x dx from 0 to 2, we're going to use a right Riemann sum. It doesn't really matter which method we use, but we're going to use that. And this area right here, this form, is based on the right Riemann sum. And notice that we at the end of this sigma notation that we're going to come up with, we have to take the limit of n approaches infinity. Okay, couple of things we need to do. Number one is finding delta x, and delta x is b minus a divided by n, so that's 2 over n. That means that our partitions is 2 over n, and our first value, which is f of x1 times delta x, which is 2 over n, this rx1 is actually 2 over n. And then it goes and increases by 2 over n partition all the way, and we're gonna go ahead and write it up. And the way you write it, it will be f of 2 over n times 2 over n plus the next one will be f of 4 over n times 2 over n plus, and you can see what is happening. And the last piece will be f of 2n over n, because we want to get 2, right? That's our upper bound, times 2 over n. Now, when you go ahead and simplify this, actually, let's do because of the function is y equal to x, so this is our function f of x equal to x. We'll just have to plug it in, and then we'll just get it. We said, okay, so this would be 2 over n. So 2 over n times 2 over n plus 4 over n times 2 over n plus, because remember, I'm just taking the input x1, which is our sample value, but it's the right Riemann sum. That means a right rectangular approximation we are using. So that means we are actually using the next value up. So not the x0, but x1 we are taking, right? So, and then you continue that. And then the last thing that you will end up getting will be 2n. So this is plus over n times 2 over n. Let's polish that. When you polish that, you will end up getting this factor 2 over n. It belongs to every single term. So let's factor that out and let's polish that. So you will get this, and then we're going to polish that again, because you notice that there is another 2 over n inside. We can factor that out, and when we do that, we will get this form after we simplify the top, okay? And then, of course, we're going to go ahead and simplify that again, so we get 4 over n squared plus, and then the summation. And this is the Gauss sum. And if you remember, the sum in here is given by the formula of n times n plus 1 over 2. This was Gauss did this when he was 10 years old. So basically, if you want to do the math on that one, if you add 1 plus 2 plus 3 plus 4 plus 5, if you add the first term and the last term, you get 7, but you always get 7. And you notice that there are 6 terms here, but there are 3 sums. That's why the n divided by 2 is n is number of terms in that sequence. But this is from a previous grade, probably grade 11 or grade 12. But that's the form here, so we're going to use that. So that would be 4 over n squared times n plus 1 all over 2. And then we're going to simplify that. When we simplify that, you'll get 2 times n plus 1 all over n. And now we're going to go ahead and we're going to take the limit as n approaches infinity of 2 times n plus 1 over n. Okay, so once we have that, now we're going to do the math. And that is limit as n approaches infinity of 2 over n. I'm going to multiply this through, and that would be 2 over n, the last term. Okay, and this is very simply, we know that we can simplify the n and n. We know that the sum of the limit is limit of each sum, each of the terms. So in here, the limit of n approaches infinity of 2, that's 2. And then the limit of 2 over n as n approaches infinity, this limit will be 0. So that would be 0. So the final answer will be 2. And that is the area under the curve, which is in this case is the line from 0 to 2 interval, and using the definition of the Riemann sum, but as n approaches infinity. Okay, check out the next video, and make sure you do a review, put a card in or leave it in the description below for the review of the last lesson so that you keep up with the content. All right, until next time.